All right. Hello, everyone. Thank you again for your ongoing patience. Um, hopefully I will see you on Tuesday. That's a high priority for me to get there with you guys, to have an in-person day before the test. So know that that is my fullest intent, and I do believe that's going to happen. Um, so thank you. Thank you for your patience. I really appreciate it. Um, We are in the phase of preparing for our test. We're still kind of going over some material. So we started equilibrium of a rigid body. I'm going to take a look at those homework questions, but I also wanted to look at this question here. This question here, I realize that I don't want to say I'm overcomplicating it, but there's definitely another approach that you could take that probably aligns with our curriculum a little bit better. Um, I don't know if I would say that, but it aligns with this section a little bit better. And I think it's the way the textbook intended you to do it. And so I wanted to just kind of touch on that. I actually have an extra thing over here somewhere. Um, I did for my Wednesday class, like do a whole recording of going through the problem. So I can send that to you guys too, of all the details, but basically we break it into its two halves. Each half has a line of symmetry. So we get that just make sure you unmute yourself if you have a question to put in. Simplify onto, so if we look at these lines of symmetry, we're going to have balanced moments on either side. And so we can have, that would be our line of action of our equivalent force, to have an equivalent force couple system on each half. So we would have the forces that are a summation of the forces on that half. We go through to get our unit vector of our roofing is going to be what we're able to get from our geometry. Unit vector of our forces is going to be perpendicular to that. So we'll switch the two terms. So most of this we did on Tuesday as well. It's kind of recap. Multiply the force magnitude by the force unit vector to get the force vectors. We have two of them. And then we can do our cross product if we get our R value, or the distance between our point D that we're supposed to analyze, which is down here, and the point of application of the forces. We can do the cross product to get the moment. The other thing is, if it's easier for you, these are already separated into X and Y elements. So if you wanted to, you could kind of manually do a cross product by doing your forces times your perpendicular distances and adding them all together. So that would be, then you would have four forces, because this would be an X and a Y, and this would be an X and a Y. Or 4 moments from that. So where it kind of, I started deviating from the textbook solutions is, so for part A, we find an equivalent force couple system at D, which is what this is, which we just solved for. The line of action is going to be where we can move that force to have it so that there is zero moment impact. So similar to how on this section of roofing, let's go back even more. On this section of roofing, we could turn these all into one force without impacting the moment analysis of this. We could, maybe not saying without impacting it, but if we slide this down, right, we're going to have the force times a perpendicular distance from that point of application, which would then apply a rotational moment. So what I told you guys is actually like this one right here. So these are two possible solutions. We'll do this one next. This is the one I introduced to you guys already. If I go back to my original two forces, I have the equation for those two forces. The moment is going to equal 0 where these two lines of action intersect, right? Because there is going to, the perpendicular distance would then be 0. So the point of intersection of these two forces would be the line of action of your new force, or the force that has a 0 moment impact. The force where the moment would be 0, where you wouldn't have to manually add that moment in, that couple in. So to solve for this, you would solve the system of equations. There's going to be one solution that solves both of your force vectors. And that would be the point of intersection, and that would be the point that is the line of action of that force. The potentially easy, depends on the other way. We'll say the other way to do it is we're going to just move that force down. We already have everything on this point. We already know the moment applied to this point. So let's move this force down, whatever distance. Our moment equals our force times our distance. We have our moment and we have our force magnitude. So we can divide our moment by our force magnitude to get our distance of 20 feet. And then logically, if we are fixed at this point and we want a counterclockwise rotation, we would need that force to shift downwards, right? If we're focused on this point, shifting it downwards would keep that counterclockwise rotation. If we shifted it upwards, it would go clockwise. So logically, D is 20 feet below that that point D. Or the force is applied 20 feet below that point D would get rid of your need for an external couple. They look like different spots, but if we remember the principle of transmissibility, we can slide our forces forward and back along their line of action to get, right, their moment impact won't change if we're sliding them along their line of action due to the principle of transmissibility. Any questions there? Okay. Silence, I assume no questions. Okay. This is the textbook way, and what they did is essentially the same as what I just did on this one, except for they did it using the cross products, which will give you that negative notation, but it's definitely a little more complicated. Or if you're less familiar with cross products, it's a little more complicated. Okay. That all being said, let's take a look at, okay, let's do a quick reminder of the rigid body stuff, take a look at the homework questions, and then we can go into some test prep. So, static equilibrium of a particle, which was our first part of the class, means that there's no translational moment. Summation of forces is equal to 0. Summation of forces in any direction is equal to 0. When we add rigid bodies, when we're looking at rigid bodies instead of particles, they have some shape to them, some size to them, and so we now have that rotational element to it. So our static equilibrium equations go from summation of forces in X and Y and maybe summation of forces in Z to add all the summation of forces of moments, summation of moments in any of those axes along any of those axes at any point. At any point, we should have a moment of 0 when we're in equilibrium. Summation of moments of 0. Free body diagrams are even more important because we're starting to add forces that we're not seeing on our drawings, on our spatial diagrams. So in this case, we have a weight coming down. That's one that we're more used to doing already. We see that weight here. Values are slightly off, but the forces are the same. A here is a pin joint. A pin joint allows for rotational freedom. And what we want to do is put forces in where we're constraining movement. So if at A we have, right, we can't pull this. This is either bolted or welded to the wall. We can't pull it off the wall, and we definitely can't push it through the wall. The other thing we can't do is slide it up and down. So we have a constraint along the x-axis and a constraint along the y-axis. We do still have freedom of rotation, freedom of movement around that pin, meaning we can rotate. And so we do not have an applied moment there. B is a rocker, meaning we only have a force perpendicular here. It's able to slide back and forth, pulling it off the thing, questionable if that would be allowed, but we can't go through the wall. There's that constraint there. Ones that I want you to focus on here are rollers, wheels, rockers, or frictionless surfaces will only be a force perpendicular to the surface that they're hitting. Links and cables, we'll use our unit vectors, which we'll take a look at because that will be on test 2. Frictionless pins or hinges or rough surfaces. Sometimes these will look like more like a a C, tombstone or something. Like what you see here. They apply force in the X and the Y or in the lateral directions, perpendicular and parallel to the surface that they're hitting. And then the fixed support is our 2D structure that has an applied moment there. When we go to analyze our systems, to do our static analysis of our systems. First thing, identify the boundaries of your free body diagram or your analysis. And anywhere where you slice something, you're going to insert forces. So slice the pin joint, add both the pin joint forces. Slice the rocker, add the rocker force. Cut this cable, add a force of the weight. The only one here we don't have is that weight due to gravity. When we get to this point, so our summation of forces in X must be equal to 0, and our summation of forces in Y must be equal to 0. Wherever you want to start is fine. You can start with summation of forces, you can start with summation of moments, but let's just say for this one, we'll start with our summation of forces in the Y direction. We have a positive AY, we have a negative weight of the crane, and a negative weight of our load. All of those together, we're in equilibrium. So this needs to counter these two forces in order for this crane not to collapse. So this AY needs to be the sum of these two or the sum of the magnitudes. And that gives us 33.3 kilonewtons. When we do our summation of moments, you want to pick locations. You want to be mindful about where you pick your locations for your analysis. If we were to analyze, let's say we were to analyze point up here, we were to analyze this point, we would have a lot of unknown values in our moment analysis because we would have AX, AY, and B. If instead we were to analyze point A, summation of moments about point A, AX has a perpendicular distance of 0, AY has a perpendicular distance of 0, and so B will be the only unknown value in that equation. B times its perpendicular distance of 1.5, 9.8 times its perpendicular distance of 2, and 23.5 times its perpendicular distance of 6. If we're fixed at A, our B force is going to counter our other two forces. So we're going to have, these would go clockwise, so we'll do those negative. And solve for B is 107 kilonewtons. Same thing. So once you get that, right? If we had AY and B, we can solve for, once we have B, we can solve for AX, right? There are only two X forces here, and it is our reaction forces. So they need to equal the inverse of each other, right? They need to have the same magnitude and opposite directions. So AX we can solve. If we wanted to, we could do another summation of moments about point B, and that would get rid of B from our moment analysis and AY from our moment analysis, or they would be multiplied by a perpendicular distance of 0. And so we would only have AY, AX in there. Are there any questions up to this point? Cool. Let's take a look at the homework questions for the new stuff. And start looking at things. So one thing I'd like to bring up just as a kind of like, you're going to see this a lot, and this is why. And of course, now I don't see it in the homework questions, but you will start seeing combinations of pin joints and either rockers or rollers or wheels or something of that nature. When we look at bridges, massive bridges, we're going to have usually different supports on either side. There's going to be some element of This is not on the test or in the class. It's just kind of bonus engineering stuff. You're going to have expansion and contraction of your bridge due to temperature, environment, thermal expansion. So if both sides were fixed, we're going to get a crack somewhere in there. It's going to impact the integrity of the bridge because both of these would be applying those X forces and they may be like over constraining it, not allowing for room to breathe with expansion and contraction. So if you have a pin joint on one side and a roller on the other side, that roller can do those small lateral movements to adjust for that expansion and contraction. So you will see pretty frequently pin joints in rollers or pin joints in wheels or things, that kind of combination of things. Like I said, not in our homework though. It'll be in the next one, I think. Okay. So this one, a 10-meter beam AB rests on but is not attached to supports at C and D. Neglecting the weight of the beam, okay, no weight, determine the range of values for P for which the beam will remain in equilibrium. So our free body diagram, we would expect to look something like this. With a force of P, unknown magnitude, force of 4 is in the halfway point, force of 20 is at B, C is here, and D is here. You can logic, usually within reason, sort of logic, the direction of your forces. Like we have all these negative Y forces, we need to balance that with positive Ys. So CY and DY are going to be, we assume, positive. If we're wrong, we'll get a negative value. If I wanted to start, add your measurements into your free body diagram too. I'm just struggling with the annotation thing. So what else we have? We have to then approach it with summation of forces and summation of moments. We cannot go in with a summation of forces in the Y direction because we have 3 unknown Y forces, P, C, and D. Let's come up here. If we do our summation of moments about C, we'll come up with an equation that has both P and D in it. And then if we do so basically you're going to want to choose 2 points. And you have 3 options for those 2 points. Either A, because that would get rid of your unknown value of P, C, because that'll get rid of your unknown value of C, or D, because that'll get rid of your unknown value of D. If you do 2 of those analyses, you'll end up with 2 equations. You can solve your system of equations. We'll take a look at that more fully, but just kind of as a prep. Most of the focus for these, if you have questions, definitely ask. But I'm mostly focusing on the free body diagrams, I think, here. So we do have some time for our class. I mean, our test prep. Okay. So here, our boundaries are going to cut AB, and they're going to cut the fixture at C. C is a pin joint, so we're going to apply a CY and a CX. Pin joints have 2 forces applied to them. And so this one I'm going to add the force to AB. And so usually pin joints are a good spot to do your summation of moments because there are 2 unknown values there on most problems in this class specifically. Okay. This one here. Sometimes our forces do go through, I don't know how to phrase this. That principle of transmissibility can help us in that we can pull EX, right? If we were to analyze point F, EX would have a moment impact of 0. Even though it feels removed from that, that's that principle of transmissibility that was implied our forces. Because we're only concerned about the perpendicular distance, right? I think there's a truck somewhere. Might be an old PowerPoint. But there's a truck somewhere in the slides that has like one version it has a force pushing, one version it has a force pulling. Whichever you were to do, the summation of the force is going to be positive x direction. And if you were to analyze any other point, either up or down from that, the perpendicular distance is going to be the same. So here, E would be a great point to analyze because you get rid of moment impacts EX and EY. F would get rid of DF and EX. D would get rid of force DF, this 150 kilonewtons, and EY would go straight through that. And so there's just different ways you can, so pay attention to the line of action of the forces, I think is my point here. Pay attention to the line of action of the forces. So here A and C are both going to have pin joints in them. However, the force from this pin joint is coming from this thread here. So if we wanted to create boundaries for our system, going all the way around here, we can turn this force into this. We know we can establish or we can figure out the unit vector of that from our geometry. And that will give us our proportion kind of. So we know that A is going to have an AX and an AY. If we wanted to, we could have extended our boundaries to go like around AY and cut there. But if we did that, then we would have an X and a Y, an X and a Y. And this one, we do have information about the constraints of the direction of it. Because of that AB line, we know that the force has to go along that line. That's the only force that's impacting A. And so if we were to choose that as our boundary, we're missing some information that's going to help us solve this. So this one, especially be cautious about how you pick your boundaries, but also know that the X and the Y forces here, while if you were to separate them again, that X element is still going to have a moment impact of 0. Are there any questions on this one? Analyzing the moment at B would get rid of AB and it would also get rid of CY. So analyzing the moment at B will give you only one unknown being CX. So that would be how I would start it. This one, let's take a look. This one has a similar concept with the thread. Wait, here we go. There we go. Okay. So our next one, we have a hinge, we have a rod AB hinged at A, pin joint hinge, attached at B to cable BD. So don't forget about the unit vectors and having constrained directions. So DB, we know the direction of DB, we also know the direction of AB. Knowing that D equals 200 millimeters, determine the tension in cable BD and the reaction at B. Similar type of thing, we're going to split these. So you are going to have technically they're both pin joints. And so they would apply an X force. They will have that, the linkages are going to be pulling in whatever direction they are. So we have those constraints of the directions. Free body diagram is going to depend on your boundaries, but ultimately we want to remove it from the wall. That's our priority, removing it from the wall. And so we'll add our AX and our AY and our DX and our DY. If we wanted to though, we could just analyze this bottom linkage and have this force here then constrained in its direction as per its geometry. Questions here? We're going to switch soon to test stuff. This one is two separate pieces. Here we go. This one is two separate pieces. We have a handle that goes around this and down, and then we have a spinner. A spanner is shown to use is used to rotate a shaft. For some reason, I always think of this one as a pizza cutter, though, probably because we're looking at it 2D in that like cut element. Pin fits in the hole at A. So A, there's a pin, while a flat frictionless surface rests against the shaft at B. Flat and frictionless, meaning it doesn't allow for flat and frictionless. It doesn't allow for perpendicular movement, but it does allow for sliding. Our frictionless surface up here. Losing myself. Okay. 300 Newton force applied at P, or P is applied at D. Find the reaction at B and the component of the reaction at A. So ultimately, we want to separate these two elements. If we cut out this middle circle, right, this part that is focused on C, we have an element where it would touch A. Even though I keep struggling to get to the next slide, our boundaries of our free body diagram are kind of like that. So we have forces at A, because the only thing, and force at B. At B, remember, it's going to be perpendicular to that contact point. Note too that B would apply its force along the direction of the handle. So if we were to find our moment here, we would get rid of two unknowns. A is going to have two forces, and if we were to apply a moment there, we would get rid of those two unknowns. There is a little bit of trig in this one as well. Our next one, our last one for this homework assignment. There we go. A force P of magnitude 90 pounds is applied to ACDE, which is supported by a frictionless pin at D. Pin at D. So saying frictionless for the pin is just saying that there's not a moment applied. If we had a pin joint and we were assuming friction, we would have a moment that doesn't keep it in equilibrium, but just add some resistance. That's going to be probably not for a little while. I don't think even dynamics you would really go into that yet. But so that's where that frictionless is. It's like saying frictionless pulley, you're going to see it. It just means assume that there's no extra little forces in there. Since the cable passes over a small pulley at B, the tension may be assumed to be the same in portions A, B, and BE. So this is all one thread, and because that pulley is frictionless, there is no loss in the tension. For the case when A equals 3 inches, determine the tension in the cable and the reaction at D. So if we were to look only at this linkage, what we would do is cut this thread here and have a force there, cut this thread here and have a force there. Remember, if we cut threads, usually we're going to want to have something in tension because ropes go slack when you push them in. So we kind of already have a hint as to what direction that force is going in. Okay. If we were to analyze point B here, this force goes through that and this force goes through that. So if we were to analyze point B, we could get rid of the impacts of both of those forces. I'm going to say point B is like the far corners because we want to be even up here. If these had a sharp meeting point, that would be what I'm talking about. But it's where our geometry is labeled, the 12 inches up and the 5 over from A. So analyzing the moments about B is going to get rid of those unknown values. D, we have a pin joint. So if you did the moment, we want to apply a force perpendicular to the surface and a force parallel to the surface, so an X and a Y. And so anything along this line is also going to get rid of anything along this line is going to get rid of dy. I was thinking there was a y element to E, but there's not. But it would get rid of, if you analyze D, you would get rid of both of those unknown values. Analyze down here, anywhere down here, if you analyze A, let's do A. Analyze A, we're going to have a 0 moment from P, and so that'll get rid of that unknown value. And then we'll also have a 0 moment impact from this. So we would only have one element of tension from our E element. Okay, there's a lot of different ways. There is creative freedom, maybe not creative freedom, but some freedom in how you want to approach these, and a ton of different ways you could solve them. Any questions on the next homework? Okay, cool. Test 2. Let's start here. Let's not start that. Start here. Okay. So your 3 main questions for this test. It is another 3-question test. The first question is going to be using unit vectors. You're going to have problem geometry, so an image in your problem. I do believe it's 3D. I believe both of these are 3D. This comes from an image as well. Use the problem geometry to find the unit vector of the wire. So you'd have to find the positioning of the wire, the location of either end, subtract them to find the vector between them, find the magnitude of that vector, and divide the vector by that magnitude to get the unit vector of that wire. The reason we do that is because our force goes along the line of action of the wire, or the wire is the line of action of our force. We even see that here in our new reactions chart or reactions table. So once we get the unit vector of the cable, then we can multiply that unit vector by the force magnitude to find the force vector. And that will be your first type of problem. Your second type of problem, any questions on the first one? Second type of problem is going to be using the dot product method. Use the dot product method to determine the angle formed between 2 cables. So again, you're going to have to find, you don't have to find the unit vector of the cables, but you do have to find the vector that describes the cables. So it doesn't have to be divided by the magnitude. It could be just the vector itself. But we're going to go into our, and I'm not including it probably in this one. Here it is. The product. Angle between 2 vectors. Definitely want to have this slide with you. This is the part specifically I'm talking about. P dot Q is equal to P times Q, the magnitude of P times the magnitude of Q times cosine theta. Dot product is multiplying like terms together and then summing those like terms. Dot product is also known as the scalar product, meaning it is scalar. It does not have a direction. It only has a magnitude. So ultimately you do the dot product, you divide it by the magnitude of the two vectors, and that is going to equal cosine the angle. So if you were to do the inverse cosine of all of this, you'll get the angle between the two vectors. Questions there? The last one, use a cross product to find, we'll go into example problems too though. Cross product to find a moment. You're going to be given a force in its vector format, the point that that force is applied to, and then you need to use the cross product method to determine the moment produced about the origin. So the first thing we're going to have to do is find our R vector. Our R, I'm not going to go completely appropriate with the vector things just for time, but our R vector is going to equal the point of application minus the point of analysis. In this case, it's easy. Our point of analysis is the origin. And so we can just say that, right, -1 minus 0 in the I direction plus 2 minus 0 in the J direction plus 1 minus 0 in the K direction. So ultimately, our vector looks a lot like our point, except for our point is, except for the difference of between being a point and being a vector. 2J plus K. Okay, so that would be our R vector. The next thing we're going to do is we need to set up our matrix. Matrix, we want a 3 by 3 here. And so our first row is going to be our unit vector symbols, I, J, and K. Our second row is going to be our R value. Most common mistake for this question is putting the force vector in your second row and then the R vector in your third row. And if you do that, you will get the wrong answer. Dot product, it doesn't matter which order you put them in. Cross product, your order is important. So our R vector here, -1, 2, and 1. And our force vector, 2, -1, and +3. 2, -1, and +3. We then do our positive values going in this direction, and either negative values or subtract the product going in the other direction. So I'm going to start with my negatives. New equation in here. So first thing would be I times 2 times 3, so 6I. J times 1 times 2 plus 2J. Plus K times -1 times -1. Negative times negative is positive, so +1K. Now we're going to go back and we're going to go in our negative direction, which is going to be this way. I like to start with the I because of just lining things up and keeping things straight, but you could also picture this way, negative. Okay, so I times 1 times -1 is -1I times -1, because we're in our negative direction, is +I. J times -1 times 3 is -3J times -1 is +3J. K times 2 times 2 is 4K times -1 is -4K. And so our final answer here, the moment would be 6 plus 1 is 7I plus 2 plus 1 is 3J plus 1K negative 3k, minus 3k. These are not the exact values, obviously, but that is the idea of it. Questions there? Okay, cool. Let's look at, so I listed some example problems, and I pulled these my first year of teaching the class. So some of them are good to work with. Some of them have a little deviance, deviation. So one thing to note, this 319, 320, those are really good for practicing your cross product question. The only difference is you're given R instead of the point of analysis and the point of application. But if the point of analysis were to be the origin on the test, if it were to be, then your R value is going to have the same terms as your point of application, right? Point of application minus point of analysis is 0, 0, 0. Then we have our vectors. So these ones are good to practice. Just noting that one little change. This one I think is not the best one that you could practice. I think this is one that I probably shouldn't have pulled. It's not that it is relevant to our class and what we've gone over. But the geometry is just a little, I don't know. It doesn't, if you're gonna skip any of these, I would probably skip that one. Scalar product. So your scalar product is not alone a scalar product question, but you do need to know how to do a scalar product or a dot product in order to find the angle between two vectors. So 35 is a good one to practice. The angle between two cables, 37 and 38 are two good practice ones. I know sometimes I will hint at exact questions. None of these are exact questions. Not that I would hint at, maybe, but that the lost my train of thought. That it would be in the review somewhere. And that's not necessarily the case here. Let's look at some problems here. So the first ones are the ones we pulled. 21, let's get rid of. These ones. Okay, so what I did miss too in the questions that I had listed there are there's not really any unit vector questions, and there is a unit vector question on the test. So good questions to practice for that would be 85, 86, 89, and 90. I saw it was here. So week 5 is definitely a good one to print. In general, not necessarily every slide, but like this question I fleshed out pretty good. The only like complication with this question is that we had a little bit more of a complex system of equations at the end. So the final step of solving was a little bit harder, or the fact that we had unknown tension values also, whereas the test question, once you get to this point, you're given the tension value, so it's just a matter of multiplying the unit vector by the tension. But what I definitely would have on, if you're gonna bring a cheat sheet or your notes, whatever, this top corner right here, this unit vector equals the distance vector divided by the distance magnitude. Distance magnitude is the square root of the sum of the squares. And then our force vector or our tension vector is equal to our tension magnitude times its unit vector. This is our amount information, our direction information, and this is a combination of the two. It holds everything. So know that the end of this problem is complicated. And that's not something you would expect to do on the test. But the unit vector element is very relevant and fleshed out here. So if you're struggling with unit vectors at all, I would go look at this one. There's also slides on the cross product itself that walks it through, and that has it. There are also YouTube videos that are really helpful. These guys, Khan Academy, Practical JMT, and the Organic Chemistry Tutor should all have cross product videos and dot product videos. They should have both. Know this equation. Let's do one of the dot product questions. These ones. Three cables are attached to the top of tower A. Determine the angle formed by AB and AC. So I want to cut them around A, and I want to go AB, and I want to go AC. So I want my tensions to be going in complementary directions so that I get the smallest possible angle. If we were to have one this way and one this way, we'll get an angle between them, but sometimes we'll get like this angle between them. Don't hold me to the exact specifics of the directions and angles, but you do want them both to be going as if you were cutting them, analyzing point A. So I need to know the position of A. This might be easier. A is it's on the XZ plane. I'm sorry, it's on the y-axis. So its X and Z element are 0. Its Y element is 48 meters. B is X value of 16, Y value of 0, 16, 0, and a Z value of positive 12. And C is going to be an X value of 16 again, a Y value of 0 again, and this time our Z is going to be negative 24. Any questions there? Okay, so AB is going to equal, I believe it's B minus A, but sometimes I do get it wrong, but I'm going to go with B minus A for now. So B minus A, 16 minus 0 is 16, 0 minus 48 is negative 48, and 12 minus 0 is 12. Square brackets indicate we're now in a vector, describing a vector rather than a point. So let me make sure I got my sense right there. I want from A to B, I'm going to be going positive X, negative Y, and positive Z, and that's what I'm seeing here. If I had done A minus B or switched my things wrong, I would have gotten it reversed. I could look at my problem and logic it out that what direction the vector should be going in. So let's now do AC. So we want to do C minus A. C is 16 minus 0 is 16. 0 minus 48 is negative 48. And negative 24 minus 0 is negative 24. Again, you can check that as well. So our vectors P and Q are now vectors AB and AC. We need the magnitude of each, right? Magnitude is the square root of the sum of the squares, and I'm not, I don't want to do that right now. So I'm going to scroll and I'm going to cheat on that one. So vector square root of the sum of the squares. Square root of the sum of the squares, we can get each vector's magnitude. And so we can set our dot product of the two equal to the magnitudes of each. times cosine the angle between them. Let's go back up. I think I switched questions in my head and started thinking this was a cross product question. Dot product of AB and AC. Now that we have AB and AC values, our X values multiplied together are going to be 16 times 16. 16 times 16. Remember, this is a scalar product, and so there is no vector there. 16 times 16 plus their y elements multiplied together. 48 times 48. Negative 48 times negative 48. I'm going to just call it on this. I'm going to G on their stuff. And then the 12 times the 24. Sum those four elements together. This is the dot product between the two. 16 times 16 plus 48 times 48 minus 12 times 24 will get you your dot product. Divide that by the magnitude of each. Do the inverse cosine of that value to get the angle between them. Questions on this one? 38 is similarly structured, so if you want to practice one, you can. If we were to, let's say the question instead was find unit vector for B, AB. What we would do then is we would take our vector AB and divide it by the magnitude of the vector. So we take each of these terms and divide it by the magnitude. So we'd have 16 divided by 52 in the I direction, minus 48 divided by 52 in the J direction, plus 12 divided by 52 in the K direction. And then if we were given the tension of the force or the tension of the thread, we could then multiply that by the unit vector to get the tension vector. Let's go down here. So here, instead of it being AB, our vector is BG. This is the geometry of BG. This is the magnitude of BG. To get the unit vector of BG, you would divide the geometry terms by the magnitude. And then to get the tension vector, you would multiply the tension magnitude by that. Any questions here? Okay, so I'm going to call it, and then I will see you all on Tuesday. And we'll be ready to go for our test on Friday. Okay. All right, cool. All right, thanks, guys.